Hi, my name is Richard Gonsoulin, and I'm here with both Bryson Darr and Diego White. And today we're going to be discussing and explaining our solution for the Energy Harvester project. Now, going into the project, the customer had asked us to design a mechanical energy harvesting device that captures and, well, uses otherwise unthought of or unused sources of energy throughout Patrick F. Taylor Hall. When we were deciding on our concepts, or rather coming up with our concepts, we wanted to capture energy from an unused or otherwise wasted source that people might otherwise not think about. We wanted to convert that energy into electricity efficiently and effectively, and we wanted to do something with that electricity that is fun, creative, or otherwise interesting to look at. Uh, our first idea was a idea that we had for a wind tunnel. Essentially, we would create a device that would capture energy from the opening and closing of doors in frequented areas around the building, specifically the Panera Bread, just because of how many people go in and out of there every day. Uh, while this would have a very high interaction rate, and we would be able to collect a lot of data other than just the energy, being, you know, just foot traffic and otherwise how many people frequented the area, we decided against it because the door would open outward, which would interfere and give us a lot of inconsistent data and energy. The airflow wasn't concentrated enough to generate, or we wouldn't be able to concentrate the air into a tight enough area to essentially generate what we needed to. And the doors also closed too slowly to generate anything meaningful. We never really created sketches for this device because we never really got very far with it, but we quickly moved on to other things after we had essentially shot this one down. Our second idea was to attach some kind of device to the push door of a vending machine to generate just mechanical motion to sort of like ratchet up energy with a gravity battery. Uh, while this would have a lot of interactions, we wouldn't really be able to predict how many people would go to the given vending machine at any given time on any given day. And while this did show promise, we never really fleshed it out enough. Not to mention, it wouldn't really be able to capture as much energy because it's not a very wide range of motion. It wouldn't be able to uh, generate that much power. The device that we did, or rather the concept that we did decide on, was essentially a shaft that we would mount above a door with two spools on either end of it. The door opening would pull on one of the spools and unwind it, and on the other end it would wind up a weight that would essentially, again, another gravity battery. And this design was initially a lot more complicated because it had ratchets that would essentially allow the shaft to only spin together in one direction, but would allow the spool attached to the door to retension itself automatically. And we would attach to the other end a escapement mechanism that would uniformly distribute energy to the generator, which would generate electricity. And for that, we would use either a light or a buzzer, something of that nature. Now, we initially had to simplify this design because it was way too complicated for us to assemble on short notice and required a lot of very niche parts that we would have to special make or print. So we simplified it to just being a single shaft mechanism with no kind of ratchets or anything fancy like that, just two spools, one spool attached to the door, the other one attached to the weight, and we would attach a fan belt to the actual central shaft and wrap that around the generator to generate energy on the fly, sort of like a lawnmower's ripcord or something of that nature. The shaft was a PVC pipe, and the spools were just normal plastic spools that you would normally find around party ribbon or something of that nature. And the mounts were specially designed and 3D printed with liquid resin. While they did have some deformities when they initially came out of the vat, those deformities didn't really have an effect on the final product. So everything turned out generally well.
So, in order to properly show our conversion from mechanical energy to electrical energy, our group decided that a door light would be the most efficient way to show that conversion. Um, with the idea of a door light, we our group had the idea of basically you pull the door open, and as you pull the door open, it converts that energy into electrical energy, which powers on a door light. And the reason for our door light was like in case of emergency. So like let's say like all of PFT power goes out, and like it's dark, and it's like there's no lights. So basically, as you open the door, a light is turned on, and we basically that was basically our justification for having that light. However, it wasn't really like deemed interesting because our tiny like LED light, obviously it wasn't enough to power, or it wasn't enough to like act as like an emergency light. So we decided to pivot to a door buzzer. And so the buzzer basically works the same way as the light, but instead of, lighting it up, we the buzzer will act as like a signal when someone opens up the door. This is a lot easier to justify simply because this buzzer acts as a way to attract attention to residents of PFT, and also, as you open the door, it will literally like alert people that people are coming in. So one way we use this, like an ingenious way of like thinking of it is like you open the door, and like a buzzer goes off, and like your teacher that's like waiting for you, or like that's in the class, it's like ready to mark like who's like he's ready to mark who's like in class in attendance. So let's say it's already like past time to like let's say it's already like past attendance time. Someone opens the door, the buzzer goes off. The teacher already knows who's late and who's not. So that was our justification for our practicality. Um, how would we have calculated the results? Was using a simple equation. The tension of the string times the radius of the door turning in terms of theta. Um, that's the amount of work done by the door opening, and though that work is in joules, and that would all, well, not all would be converted because some of it would be used to spin our generator. So only some of it would be converted into electrical energy, not all of it. And so the buzzer requires 3 volts to turn on, and the light takes about 1.5 volts to stay on consistently. And so our apparatus produced in between 1.5 to 3 volts because we were able to turn on the light pretty consistently, but the buzzer was only able to come on about once or twice. So that's how we got the estimates for our for how much energy our apparatus produced.
Okay, so for the bill of materials, our total was $55.15, and we used mostly materials that were cheap, but the majority of our cost was our two 3D printed mounts, and it was $26. But the rest of the materials, they weren't they were cheaper, but they should last for a while. So it would be able to last a week, which is one of our requirements in PFT. Some setbacks that we had while designing our project is that our first motor that we used, Trevin bought it, and it didn't actually work for some reason. So we had to go and find a new one. And the second motor that we had, it was smaller than the motor that we were given. It was smaller than the motor that we were given, and so it wasn't producing enough volts. And also, it had a gear stuck on the shaft of it, which made it harder to incorporate. Um, the the grooves that we had on our PVC, or on the grooves on the mounts, weren't deep enough because I didn't design it deep enough. So the PVC pipe was falling out of our when the apparatus spun, the PVC was falling off of the mounts. So we had to design a little tape like thing so that it wouldn't fall off. And also the harvester, it was only turning on when when the door was closing instead of opening, or doing both. So it was only doing it half the time, which isn't what we designed it for. And also the door was closing too slow, so the motor wasn't spinning fast enough, so the light and the buzzer weren't working consistently. And then some improvements that we can make on our design is that we should have just taken the whole thing back to the understanding the problem part of the design process, because we didn't come up with like the best solution, I guess. But also we could have found a different door that would produce more mechanical energy, which would spin the motor faster, because the door that we chose was closing too slowly, so it wasn't spinning the motor fast enough, so the light wasn't turning on, or the light was flickering on, and the buzzer was not even turning on because it required too many volts. Also, we should have had a better belt rotation that converted the rotation of the PVC pipe into rotation to the motor. We used a rubber band to spin the motor, or to connect the PVC to the motor, and it was falling off because it just wasn't connected properly. So we weren't getting the best and optimal electrical output consistently. Also, another improvement, like I said, the wall mounts, the grooves weren't deep enough. We had a second 3D printed piece, but we didn't have enough time to 3D print it, so we had to, so we didn't have enough time to 3D print it, so we didn't have enough time to 3D print it, so we had to make a rainbow thing out of tape to hold it in. But we had two pieces, but we didn't have that, so it just wasn't working properly. And also when we were making it, the spool that we had, there was too much string on it, so we cut the string off, and then that caused the radius of our spool to be too low, so the weight that we were using couldn't rotate the spool, so it wasn't spinning, and that's one of the main reasons why our thing wasn't working anymore. And then our house equality, here it is. We didn't try over constraining ourselves, so there's not too many things, and that's our presentation. Thank you.